So for this one, we're going to talk about linear momentum. Linear momentum was first based off of Newton's second law. Newton's second law that said that net force is equal to mass times acceleration was a simplified version of what he actually wrote in his book. He actually talked about the net force was related to something called momentum. And momentum is also a vector, meaning it has magnitude and direction. He said that net force was equal to the change of momentum over the change in time, not so much mass times acceleration. And the way you find the vector momentum is simply by multiplying the mass and the velocity of an object. So net force is equal to the change of momentum over time. And the change of momentum is the final momentum minus the initial momentum. And again, since how do we calculate momentum is mass times velocity, we can say that the final momentum is the mass times velocity final minus the mass times velocity initial divided by time. If we take out the mass, since we assume that the mass is constant, we can rewrite that equation as net force is equal to mass times v final minus v initial over time, which is the same thing as saying mass times acceleration. So that's how we got that simplified version of it. Put the little vector sum because the acceleration is a vector. So our real net force equation is really equal to the change of momentum over change in time, and that's our algebra equation. For the AP physics, we have to take into account that we're going to have to use some calculus. Now, since net force is the rate of change, meaning the slope, right? It's how quickly the momentum is changing with respect to time. If we take the derivative of the net force with respect to, if we take the derivative of the momentum with respect to time, we get the net force, right? Because the derivative is used to find the slope. And that helps us find the instantaneous, the instantaneous net force. So if we're ever, which we'll get into later, and we'll get into problems and examples, which will hopefully make it make more sense. Before we start doing some extra problems, we're also going to talk about impulse. Impulse is a relationship between the change in momentum. In reality, impulse, which is represented by the symbol J in your equation sheet, which is also a vector, is a fancy way of saying the change in momentum. And it's also part of the impulse momentum theorem that we'll get into later. Since from our last, we found out that the net force is equal to the change of momentum over time. Now, we say it's the average net force because when something is hit, like a ball hits against the wall and causes it to feel a force, the force felt by the ball is not constant, meaning when the ball makes contact with the wall, the force it feels varies with time. And that makes it very, very difficult to calculate. So we typically say the average net force that the ball experiences over a certain length of time is equal to the change of momentum. So the change of momentum, if we take the average net force that a ball experiences when colliding into a wall and multiply it times the time that the ball is making contact with the ball, we get the change in momentum, which, like we said, is also equal to the impulse. So the impulse momentum theorem says that the impulse is equal to the average force times the amount of time that that force is acted on the object, and that'll tell you how the object's momentum changed. Now, if the net force varies, which it does, with time, and since the impulse is a product of net force and time, and usually when we associate the product, we associate the area underneath the curve. Now, this is calculus, so this is mainly for AP. We can say that the impulse is equal to the integral of the force with respect to time over the intervals of whatever time you're looking at, from 0 to 1 seconds or 0 to 2 seconds, depending on how long it's contacted. And that will help you calculate the impulse felt on the object. And this is the equation that shows up on your equation sheet. So if we had a graph of force versus time and we drew the curve, the area underneath the curve would equal your impulse. And we'll get into some of those problems as well. But let's start off with some of the basic ones. So let's look at this problem first. It says a 46 kilogram skater, they tell you the mass of the skater, and he's pushing off against the wall, which propels her backwards, and they give you the velocity that is experienced because of that push. They also tell you how long the wall is in contact with the person when they're pushing. So our givens are the velocity, the time, the average force felt is what we're trying to calculate. So for this, we'd use our impulse momentum theorem. So we use the impulse momentum theorem, and instead of we rearrange it, and we can figure out that the change of momentum over time is equal to the average net force, and we know that the change of momentum is the final minus the initial. The initial is 0 because we're assuming this is the point where the person's pushing off the wall before the force is exerted. After the force is exerted for those 0.8 seconds, the momentum is the mass, which is 46 kilograms, times the velocity. So the final momentum is 5.52 kilograms meters per second. Now there's no real specific unit for momentum. Momentum is simply the product of its two units. So when we give the units for momentum, they're typically in kilograms meters per second. So the change in momentum, which is the final minus the initial, is just 5.52 kilograms meters per second. We plug that back into the equation, we divide our change in momentum divided by time, and we get the average net force. Now, this was the change in momentum of the person. So what we calculated was the force exerted on the person that caused that change of momentum. But what the problem is asking us to find is find the magnitude and direction of the average force she exerts on the wall. So we need to, in order to find the force exerted on the wall, we use Newton's third law that says every force has an equal but opposite reaction. If the person, the skater, feels a force of 6.9 newtons to the right, it's because the wall experienced a force of 6.9 newtons to the left. So the actual force she exerts on the wall is 6.9 newtons to the left, or we can negative 6.9 newtons. And we kind of got a little farther ahead than we needed to. And that's our answer. The next problem, number 5, we're given the mass of a volleyball that is experiencing a change in velocity after being spiked. They tell us the initial velocity is 4 meters per second. The final velocity is negative 21 meters per second because it's being hit in the opposite direction. What they want us to find is the impulse that the player applies to the ball. Now, we don't have any information about the player. All the information we have is about the volleyball. But if we can calculate the impulse that the volleyball experiences, then by Newton's third law, we can figure out the impulse that the player who hit the volleyball experiences. So our solution again is to use our impulse equation, which is equal to the change of momentum. So our impulse is equal to our final momentum minus initial momentum. So we're trying to find the final and initial momentum of the ball. The final momentum of the ball is just the mass times the velocity final, which gives us our momentum. And the initial is the mass times velocity initial. Now keep in mind of the signs, because these are vectors, it's really important. Remember, the final momentum is negative because it's of its direction, and the initial momentum is positive because of the direction of the ball at the moment. So when we check our impulse, we need to make sure to put those signs correctly. So we have negative 7.35 minus positive 1.4, which gives us negative 7.8, negative 8.75 kilograms meters per second. Again, though, this is the impulse on the ball, not the answer we're looking for. The answer asks us to find the impulse experienced by the player. But since by Newton's third law, we can just assume that the impulse on the person is the opposite of the impulse that was created on the ball. So the impulse the person experiences is positive 8.75 kilograms meters per second, or we can say 8.75 kilograms meters per second to the right. For the second to last question on the video, we have number 11. Now in number 11, they're giving us a bunch of information. We have a student that falls from rest and hits the ground and comes to rest, obviously, when he hits the ground. They give us the mass of the person. They give us the final velocity when he hits the ground, which is 0 because he hits the ground. And the average felt when hitting the ground is 18,000 newtons. And the time that it took the ground to slow the person to 0 meters per second was 0.04 seconds. Now, what they want us to do is they want to know the height of the fall. Now, there's a lot of information we need to find before we find the height of the fall. The first thing we want to try to figure out is what velocity did he hit the ground with. So, since they give us the average velocity, we can use our impulse or momentum theorem, or we can just simply get the change of momentum over time. And using our average force that gives us in the problems, we can calculate the initial momentum. Because the person after he hit the ground came to rest, his final momentum was 0. So that means the change of momentum is just the negative of the initial momentum. So when we plug in our values, we end up calculating that our initial momentum is negative 720 kilograms meters per second. And since we know the mass of the person, we can actually calculate the velocity at which he hit the ground. So we calculate that he hit the ground at about 11.43 meters per second. It's negative because he's hitting the ground and his velocity is pointing down. Now, so he hit the ground at 11.43 meters per second, and he was in free fall, and he started from rest. So we can use our kinetic energy equation and then use potential energy to find out what his height was initially, or we can also use our kinematic equation. So if we use kinematic equations, we say, well, his V initial was 0 because he fell from rest. His final is negative 11.43 meters per second because that's the velocity he hit the ground with. And we're trying to find our displacement, so we use our Vf squared equals V initial squared plus 2ax equation. We plug in our variables, and from that point we solve for x, and we find out that he fell from a height of 6.65 meters. So that actually becomes our answer, and then we got to move farther off. Our answer for the last problem before we move on was 6.65 meters. For our last problem of the video, we have a situation where we are dealing with two different joggers. And not just that, the thing that's different from other problems we've done so far was that this is also a two-dimensional problem. They give us a bunch of information about the joggers. We have jogger 1, they give us his mass, they give us his velocity, and his direction. Since I know this is going to be a two-dimensional problem, it's nice to separate everything into its x and y components. So if he's moving 2 meters per second east, his x component is positive 2 meters per second, and his y component is just 0. For jogger 2, they also give us his mass, they give us his velocity. His velocity is acting at an angle of 32 degrees north of east, and they tell us that he's moving at 3 meters per second. So we use trig to break that up into its components, and we find out that his x component is he's moving plus 2.54 meters per second in the x direction, and positive 1.159 meters per second in the y direction. So that's pretty much what's given to us, and a little bit of calculations involved. So for our solution, since we want to find out the total momentum that these two joggers are feeling, we have to find the momentum of each jogger. Once we find the momentum of each jogger, we can't just add them out because they're vectors. The way we add up vectors is we have to break them up into its x and y components, add their x's, add their y's. So jogger 1 has a momentum in the x direction of 170. His momentum in the y direction is 0 because he has no velocity in the y direction. So his momentum can be written in vector notation, just kind of makes it easier for when we add them, as 172 kilograms times meters per second in the x and 0 kilograms times meters per second in the y. We do the same thing for jogger 2. Jogger 2, we find his momentum in the x, which is 139.7. We find his momentum in the y by multiplying his mass times velocity in the y, and that gives us 87.45. We kind of neatly write it down in our vector notation. Then we can try solving the answer by finding the net momentum. We find the net momentum by adding up the two x's of each jogger, since we're trying to find the net momentum of both joggers. And we end up with 309.7 kilograms meters per second in the x. We add up the y's, which is just 87.45 plus 0, which is 87.45. But we're actually not done yet, because the question specifically says find the magnitude and the direction of the momentum. But since I know it's x and y component, the magnitude, we can use Pythagorean theorem, just a squared plus b squared equals c squared. So our magnitude is 321.81. To find our direction, we probably want to use the inverse tangent. Since we know the x component, which is positive, and the y component, which is positive, which means the momentum is going to point north of east, we can use our inverse tangent of the y over the x to find the direction, which is 15.77 degrees north of east. So those are our two components of our answers. Net momentum felt by the net momentum of the two joggers is 321, and the direction is about 16 degrees north of east. And that finishes the first video with your introduction to momentum.